So welcome to the video. Today we are going to take a look at how to do a paired samples t-test on version 31 of SPSS. So we're going to use this test when we have a within participants or within subjects categorical independent variable comprised of two levels, so basically 2 time points, and when we have a continuous dependent variable. So for this example, we are going to imagine that we are interested in how anxious people feel before and after cognitive behavioural therapy, otherwise known as CBT. So these are their scores, their anxiety scores before CBT in column A, and these are their anxiety scores after CBT in column B. So the paired t-test is going to tell us, is there a significant difference between before CBT and after CBT with respect to these people's anxiety scores. So let's put these data into SPSS. So we'll go down to variable view, and then we're going to put before into this top row in the name column. So that's going to stand for before CBT, and then we'll put after in the cell below. So that's going to stand for after CBT. Then we'll go over to this measures column and we'll select scale, which is essentially another word for continuous. Then we can go down to data view, and we can see that before and after are at the top of these two columns. So then we can go over to this Excel file, and I'll select the top left piece of data. I'll scroll down, and then while holding shift, I'll select the bottom right piece of data. Then I'll go to Command or Control C to copy those data. Then I'll go back to SPSS and I'll press Command or Control V to paste those data. Sometimes that doesn't work, in which case you can just go to Edit and then Paste, and that should work. So one of the assumptions of the paired samples t-test is that the differences between these 2 time points are normally distributed. So we actually need to create a variable that represents the differences between these 2 time points. So to do this, we can go up to Transform and then down to Compute Variable, and then we can transfer before over here to this numeric expression box. Then we'll go to this minus symbol, so we'll click that, and then we'll transfer after using this arrow, and then we'll just give a name to this new variable or column that we are going to create. So we'll call that difference. Then I'll go to OK, and we can see that that has created this new variable for us. So if we minus 54 from 65, we get a value of 11, and then we just have the same thing all throughout this column. I've noticed here that SPSS has perceived this variable to be categorical. It might work like this, but just to be sure, let's go to variable view and let's change that to scale. So next we're going to go to analyze and then down to descriptive statistics, then over to explore, and then we can transfer this difference variable to this dependent list, and then we can go to plots. I'm going to tick normality plots of tests and histogram, and I'll untick stem and leaf. Then I'll go to continue and then to OK, and that's going to run a normality test for us. So if we scroll down a bit, we can see that we have this test of normality table, and we actually have 2 normality tests within this table. So we have the Shapiro-Wilk test on the right, and we have the Kolmogorov-Smirnov test on the left. And we typically use this one on the left when we have 50 or more rows or participants in our data set. And we typically use this one on the right when we have fewer than 50 rows or participants. So here we can see that we actually have 30 participants. So we're going to focus on the Shapiro-Wilk test, and what we want to see is that the sig value is above 0.05. So here it's 0.438, so that's above 0.05. So this suggests that the data are normally distributed. We can also take a look at this histogram. In this case, probably because we don't really have that much data, it doesn't look particularly convincing. What we would like to see is that we have a symmetrical bell-shaped distribution, but as I said, this histogram isn't particularly convincing. And whenever you're trying to judge whether your data are normally distributed by using a histogram, it's a bit subjective. So I prefer to use these normality tests because they provide you with a more objective answer, i.e. is your sig value above or below 0.05. So in our case it's above, suggesting the data are normally distributed, so we are fine to run the paired t-test. If you find that your value is below 0.05, you might consider doing a Wilcoxon signed ranked test instead, as that's the non-parametric equivalent of the paired t-test, and it doesn't make any assumptions about normality. So let's get on with running the test. So we can go up to analyze, and then down to compare means and proportions, then over to paired samples t-test, Then we can transfer before and after to this area here by clicking this button. Then we can go to OK, and that will run the test for us. And we can see, if we look at this paired sample statistics table, we have means here. So we have a mean value of 70 before CBT, and we have a mean value of 54 approximately after CBT. So we can see that people's anxiety scores were lower after CBT compared to before, but we don't yet know whether that difference was significant. So we need to look at this paired samples test table, and if we go over to the right side of this table, we can see that we have an area dedicated to p-values. So we have a one-sided p-value here, and we have a two-sided p-value, and in this case they're both below 0.001. However, it's common to see different values here, and which you should look at is determined by whether you had a one-sided hypothesis or whether you had a two-sided hypothesis. So a one-sided hypothesis, otherwise known as a directional hypothesis, would be something like: it was hypothesized that anxiety scores would be significantly lower after CBT compared to before CBT. So you're predicting which time point would have the higher or lower value. On the other hand, a two-sided hypothesis or non-directional hypothesis would be something like: it was hypothesized that there would be a significant difference between the two time points. So you're not specifying which would have the higher or lower value. So the one-sided hypothesis is more specific. So let's imagine that we had a one-sided hypothesis. We can see that the value is less than 0.001, and as this is less than 0.05, it indicates that there was a significant difference in anxiety scores after the intervention compared to before the intervention. So that's essentially how we interpret the results, but let's now take a look at how we can report those results. So we can go to this sentence here, and we can see that we've said that a paired t-test was conducted to compare anxiety scores before and after CBT. So we've just said why we did the test. And then we've said a Shapiro-Wilk test indicated that the differences between the time points were normally distributed, and then we've inserted these stats here. So we've said that W equals 0.97, and if we go back to the SPSS output and then scroll up to this test of normality table, we can see in the Shapiro-Wilk half of the table and the statistic column we have a value of 0.966, so I've just rounded that to 2 decimal places in the results section. We have a degrees of freedom value of 30 and a sig value or p-value of 0.438, and we have these values here. So here's the df or degrees of freedom value, and here's the p or sig value. Next, I've said that anxiety scores were significantly higher before CBT compared to after, and I've inserted some means and standard deviations. So here are the statistics for before CBT. So we have a value of 70.27 for the mean. So if we scroll down slightly, we can find this paired sample statistics table and this mean column and this before row. And here we have this value of 70.27 rounded to 2 decimal places. We have a standard deviation of 8.40 rounded to 2 decimal places, and that's what we have here. And then we've just reported the same values again for the after CBT time points, and we've taken those values from here and from here. Next, we have the results of the t-test itself. So we've said that t equals 11.74. So we're looking at this paired samples test table, and we're looking at this t column, and we can see that this value here, rounded to 2 decimal places, would be 11.74. We have a degrees of freedom value of 29, and we have a p-value of less than 0.001. And that's what we have here. So there's the degrees of freedom value, and there is the p-value. Finally, we have this sentence that says the effect size was large, and we've reported a Cohen's d value of 2.14, and we've said that it was large based on these criteria here. So values between 0 and 0.2 typically are considered very small effects. Those between 0.2 and 0.5 are typically considered small effects. Those between 0.5 and 0.8 represent medium effects, and those above 0.8 represent large effects. And the same thresholds apply if you have a negative Cohen's d value. So here we have a value of 2.14, and as this is bigger than 0.8, we have a large effect, which is why I've described it as large here. And just to show you where that value comes from, it's this paired samples effect sizes table. and this currency row and this point estimate column, where we have this value here of 2.14, which is what we've got here as well. So that's about it for the paired samples t-test on version 31 of the SPSS. If you have any questions, just let me know in the comments and I'll try to get back to you. Thank you very much for watching, and I'll see you next time.